Hello and welcome to IP lesson. In this lesson, we will learn about STP protocol. We spoke before about the broadcast, and we spoke before about what happened to our switch when it receives unknown unicast frame. So if our switch receive a frame on interface, it will start to look at the destination MAC address at the MAC address table. If it didn't find the destination MAC address in the MAC address table, it will do flooding or broadcasting. This is mean sending this data to all the interfaces except the one it came from. We have a new concept also, which is redundancy. So let's take a look at our topology in order to understand what is the redundancy. So in our topology, we have switch 1, switch 2, switch 3, switch 5, and switch 4. There is an extra link between each switch. So having extra link or backup link between devices called the redundancy. So networking is one of the important components for any company. For that reason, our network have to be up 24/7. So having a backup link between devices help us to achieve the 24/7 uptime. So this is sound really great, but the downside of having redundant link is the complexity. So having a backup link between our devices can add some complexity to the configuration and to our network in general. So if any link goes down, let's imagine that the link between switch 1 and switch 3 goes down for any reason. Can switch 3 still reach switch 1? And the answer is yes. Switch 3 will send the data to switch 2, and switch 2 will send the data to switch 1. Same thing for any connection between our switches. If the link between switch 2 and switch 5 goes down, the data can go through switch 3 and then goes to switch 2. So imagine how important the redundancy link for companies like Google, for example. So as you can see, if any device that is connected to switch 4 wanted to send data, it can go through path A, which is going through switch 3, then switch 1, and after that, switch 1 will forward the data to the internet. Switch 4 have another path, let's call it path B. It can forward the data to switch 2, and then switch 2 will forward the data to switch 1, and switch 1 will forward the data to the internet. So if switch 3 goes down, our data still can go through path B in order to reach the internet. This is for the devices that is connected to switch 4 and the switch 5. Switch 5 also can use the link between switch 5 and switch 2 in order to forward the data. If switch 2 goes down, we still can use path A, and switch 4 and 5 will be able to forward the data to the internet. So having a redundant link in our network is great and very helpful. But let's take a look at our example and see what can redundant link cause to our network. In our network, we have switch 1, switch 2, switch 3. There is one PC connected to switch 3 and another PC connected to switch 2. The PC that is connected to switch 3 send unknown unicast frame, so it send the data and the destination MAC address is unknown to switch 3. Switch 3 will check this data and it will not find the destination MAC address on the MAC address table, so it will do flooding. It will forward the data to the link connected to switch 2 and the link connected to switch 1. So let's focus right now with the frames that will be forwarded to switch 1, and let's call it frame X. So switch 1 will receive frame X, and the destination MAC address is unknown to switch 1 also. Switch 1 will flood the data and it will send it to switch 2. Switch 2 doesn't know also about the MAC address and will do flooding. So switch 2 forward the data to the PC and forward it also to switch 3. So what will happen is that switch 3 will receive this data and he doesn't know what is the destination MAC address and it will do flooding. In that case, switch 3 will forward the data to the PC and the switch 1, and the switches will keep repeating that process. So this process called loop. So when the network has more than one active path carrying the same information from the same source, this is called loop, and this will cause something called broadcast storm. So broadcast storm is an abnormally high number of broadcast packet within a short period of time. So you can imagine how consuming the process for our switches if we have a loop and this loop cause broadcast storm. This also can cause MAC address table instability. So MAC table instability results from copies of same frame being received on different port on the switch. So when PC1 sends the data received on interface G1 at switch 3. So when this frame received at switch 3, switch 3 took advantage of that frame and saved the source MAC address, which is PC1 MAC address, in the MAC address table, and next to it, it put interface G1. After that, switch 3 received the same frame at interface G2 with the source MAC address of PC1, which is the PC connected directly to switch 3. And right now, this is causing the MAC table instability. So before starting with STP, what about layer 3? What will happen if we have a backup path on layer 3? So let's take a look at our topology here in order to see what will happen. We have R3, R4, R2, and R1. R1 send a ping to R2 with the destination address 1.1.1.1. What will happen is that R2 routing table doesn't have an entry for network 1.1.1.1. R2 will discard this message, so there is no broadcast will happen here. So we will not have the same scenario that we have with layer 2. So what about the backup path? So for R1 to reach R3, it can go through R2, let's call it path A, or it can go through R4, let's call it path B. In that case, the routing table will not have more than one entry to a destination. So in our routing table, we will see path A or path B. So this will not cause a loop in our layer 3 network. Let's imagine that there is a loop in our network and R1 send a packet, let's call it packet 1. So this packet will exit out with TTL 255. The packet will keep looping in our network until the TTL value will be 0. So when the TTL value will be 0, it will be considered as unreachable and our router will discard this packet. That's why we don't have the loop problem that we have on layer 2. For layer 3, there is a lot of mechanism solving the loop problem, and for layer 2, we will learn about STP, which will solve our loop problem for layer 2. So back to layer 2, let's see how the spanning tree protocol will prevent the loop from our network. STP stands for Spanning Tree Protocol, and STP is a protocol that creates a loop-free environment in case of redundant link. So Spanning Tree Protocol will work in our network and will block one port in order to avoid the loop. So you can ask a question here. If we are gonna block one port in our network, what of the benefits to have a redundant link? We will see the answer for this question in this lesson, but in general, STP protocol work to block one port, and if there is any link goes down, it will enable this port and will forward the data through that port. So if the link between switch 1 and switch 3 goes down, the blocked interface, which is between switch 3 and switch 2, will move from the blocking state to forwarding, which means it will forward the data. Spanning tree protocol is a layer 2 protocol. As we mentioned, the loop happen only on layer 2. For layer 3, there is a lot of mechanism that avoiding the loop. The standard name for STP is 822.1d. There is more than one type of spanning tree protocol. There is the regular spanning tree. There is the rapid spanning tree protocol. There is MST, multiple spanning tree. And there is BVST, Bare VLAN Spanning Tree Protocol. Cisco added some enhancement to the BVST, Bare VLAN Spanning Tree, and came up with BVST Plus, which is Bare VLAN Spanning Tree Plus. This is a Cisco proprietary, which means no other vendor can use this protocol. BVST Plus is the default spanning tree protocol configured on Cisco devices. So let's see how the spanning tree protocol will work in our network in order to prevent the loop. First, STP use an algorithm called STA, which is the spanning tree algorithm, in order to define the blocked port. STP will use the STA algorithm in order to define a switch, and this switch will called root bridge. Based on the root bridge, spanning tree protocol will determine the blocked port. So there is two questions here. Are we gonna wait until the loop happen and then spanning tree protocol will work? Also, how can we define the root bridge switch? And the answer for those two questions is BBDO. BBDO stands for Bridge Protocol Data Unit. The Bridge Protocol Data Unit is a message sent between switches, contain information about switches, priority, switch port priority, and addresses. So when we bring up our switches and connect our switches, all the data will be plugged to enter our switches except the BBDO message, the Bridge Protocol Data Unit message. That way, we can prevent the loop in advance. So all the switches in our network will start to exchange the BBDO message. After our switches will exchange the BBDO message, they will start election to choose the root bridge switch. The root bridge will be chosen based on something called bridge ID. So the lowest bridge ID switch will be the root bridge. So the superior BBDO message will be the lowest bridge ID, which will be the message from the root bridge. And there is also the inferior BBDO. Inferior BBDO is the higher bridge ID than the root bridge. So what is the bridge ID? Bridge ID consists of two components. It consists of bridge priority, and this is a value assigned by STP protocol. And by default, the bridge priority is 32,768. The second part of the bridge ID is the MAC address. For classic STP, the bridge priority is just the number 32,768. For rapid spanning tree protocol, the bridge priority consists of bridge priority, which is 32,768, plus system ID extension. The system ID extension will be the VLAN ID. So if we have VLAN 2, the system ID extension will be 2. If we have VLAN 1, the system ID extension will be VLAN 1. So here is an example of BBDO message captured by Wireshark. As you can see, the bridge priority is 32,768. System ID extension is 1, which refer to VLAN 1. and there is also the MAC address. So you can ask a question here, which interface is that MAC address belong to? And the answer for the MAC address, STP doesn't use any interface MAC address. Instead, it uses a MAC address called base Ethernet MAC address. You can see this MAC address if you did show version on the switch. So let's take a look at our example in order to understand more about the spanning tree protocol. In my example here, I have switch 1, switch 2, switch 3, and there is a redundant link between the switches. First thing, we need to define the root bridge. In order to define the root bridge, we need to look at the lowest bridge ID. So first part of the bridge ID is the bridge priority, and as you can see, switch 1, switch 2, switch 3 have the default bridge priority, which is 32,768. So since the bridge priority is equal at all the devices, the next part we will look at the MAC address. Switch 1 MAC address start with 0A, switch 2 MAC address start with 05, and switch 3 MAC address start with 06. So the lowest bridge ID is switch 2. So switch 2 will be the root bridge in our topology here. And based on the root bridge, we will define the plugged port. Now our switches will start to add the root ID to the BBDU message in order for all the switches to know which switch is the root bridge. After we identify the root bridge, the spanning tree will do a calculation in order to define the plugged port. First, the STP will add the root cost to the interfaces. The root cost is a value that STA will assign to interface in order to calculate the shortest path to the root bridge. We have also the path cost. The path cost is the total root cost from a switch to the root bridge. So for interface 10 megabit per second, STP will assign root cost 100. For 100 megabit per second interface, the root cost will be 19. For interface 1 gig, the root cost will be 4. For 10 gigabit per second, the root cost will be 2. So this cost value didn't support the 100 gigabit per second interface and the 1 terabyte per second interface. For that reason, the IEEE came with a new cost in order to support the 100 gigabit per second interface and the 1 terabyte per second interface. So by default, Cisco switches will use the old cost. In order to apply the new cost, we have to put the command spanning tree pathcost method long on our switch. So let's continue with our example. In our example, switch 2 becomes a root bridge in our network. So for root bridge interfaces, the root cost will be 0. Also, the root bridge ports will be in a state called designated. After that, we need to define the root port, and the root for the tree absorb water and other useful compounds from the soil. So the tree root should be the closest thing to the soil. Same thing in spanning tree protocol, the root port is a port within the lowest path cost to reach the root bridge. So similar to the tree root should be the closest thing to the soil. The root port also should be the closest port to reach the root bridge for each switch. So let's see which port will be the root port for switch 3 first. As you can see, switch 3 have 2 paths in order to reach the root bridge. So let's assign the root cost to all the links in order to find the root port. All the interfaces that we have are fast Ethernet interfaces, so the cost will be 19. Switch 3 have a path with a cost 19 and another path with cost 19 plus 19 in order to reach the root bridge. So we have a path with 38, which is 19 plus 19, and another path with 19. For root cost, we are looking for the lowest path cost in order to find the root port. In that case, interface fast Ethernet 0/1 will have the lowest path cost and will become the root port. After that, we're gonna do the same thing for switch 1. Switch 1 have two paths in order to reach the root bridge. The first path with cost 19 and the other path with cost 38. In that case, the path with path cost 19 will win and become root port. So after we found the root port for switch 1 and switch 3, the next step to define designated port and the plugged port. And as you can see in our example, interface fast Ethernet 0/2 on switch 1 have the same cost as interface fast Ethernet 0/2 on switch 3. So how can we find the plugged port and the designated port since the two ports have the same path cost? In that case, the bridge ID will be the tie break in order to define the plugged port and the designated port. So the lower bridge ID will be preferred. In that case, switch 1, switch 3 have the same bridge priority. So the tie break will be the MAC address, the lowest MAC address. Switch 1 MAC address start with 0A and switch 3 MAC address start with 06. So switch 3 have a lower bridge ID than switch 1. The result of that is that switch 1 interface fast Ethernet 0/2 will be plugged and switch 3 interface fast Ethernet 0/2 will be designated forward. Let's take another example. In our example here, we have switch 1, switch 2, switch 3, and we have two links between switch 2 and switch 3. So let's ask a question here. If we plug the one port, is that gonna solve the loop problem? And the answer is no. So if we plugged the top link between switch 2 and switch 3, we still have a loop in our network. So spanning a tree doesn't plug one port or two ports or three ports. The plugging will be based on the loop in our environment. So in our topology here, we have two loops. And in order to plug the loops, we need to plug two ports. So let's find the root bridge first. So the bridge priority is equal at all the devices. So the MAC address will be the tie break. The lowest MAC address in our topology is switch 1 MAC address. In that case, switch 1 will be the root bridge. The root bridge switch interfaces will be designated forward and will have root cost 0. We're gonna start with the loop in interface fast Ethernet 0/1 on switch 2 and interface fast Ethernet 0/1 on switch 3. Switch 3 will have two paths, a path with path cost 19 and another path with path cost 38. In that case, the port with path cost 19 will be the root port. Same thing with switch 2. The path with root cost 19 will be the root port. After that, the bottom path have an equal root cost. In that case, the bridge ID will be the tie break. Switch 2 have a lower bridge ID. In that case, switch 2 interface fast Ethernet 0/1 will be designated forward and switch 3 interface fast Ethernet 0/1 will be the plugged port. The next step to plug the second port in order to prevent loops in our network. So here we have a question. Is interface G0/1 will have lower path cost than interface fast Ethernet 0/1? And the answer is no. The reason of that, because interface G0/1 and interface fast Ethernet 0/1 will negotiate the speed, and since interface fast Ethernet 0/1 cannot send the data faster than 100 megabit per second, interface G0/1 will reduce the speed and become fast Ethernet interface instead of gigabit interface. So the path cost will be equal from G0/1 and fast Ethernet 0/1, and in that case, the bridge ID will be the tie break, and the bridge ID on switch 2 is lower than switch 3 bridge ID, and the result will be that interface G0/1 will be the plugged port, and interface fast Ethernet 0/1 will be designated port. Let's take another example. In our example here, we have two switches, switch 2, switch 3. Switch 2 has the lowest bridge ID, so it will become the root bridge. Switch 2 interfaces will be designated forward. And right now, we need to define the root port and the plugged port on switch 3. So interface G12 is coming from switch 3 and the cost is 4. Same thing with interface G2. It's coming from switch 3 with the same bridge ID and the same cost. So as you can see, those two interfaces have the same bridge ID and the same cost. In that case, the interface number will be the tie break. So lower is preferred also. So interface G2 will be the root port and interface G12 will be the plugged port. Let's take another example. In my example here, I have switch 1, switch 2, switch 3, and switch 4. Switch 4 have the lowest bridge ID, so it became the root bridge. All the paths have a gig interface except the link between switch 1 and switch 2. So the root bridge port will be designated forward and will have value 0. Switch 3 interface G2 will be the root port because it have path cost 4. Switch 4 interface G1 will be the root port because it have path cost 8. And switch 2 interface G1 will be the root port because it have path cost 12. So after that, we're gonna choose the designated ports and the plugged port. Switch 3 interface G1 will be designated port because it have path cost 8. Switch 4 will be designated port also because it have path cost 12. And the last interface we have is interface fast Ethernet 0/1 on switch 2. As you can see in our example, this is the highest path cost interface. It have a path cost 19, and all the other interfaces have a path cost less than this. The result will be that interface fast Ethernet 0/1 on switch 2 will be the plugged port. So after spanning a tree, run, and the STA algorithm defines the plugged port, the interfaces will keep sending bbdo hello message. So what about if another interface or another link goes down? For that reason, spanning a tree will keep working and sending a hello time, and spanning a tree protocol use a timer. So we have the hello timer. Hello timer will be sent every 2 seconds. And it's the time between each hello bbdu message. We have also the max age time, which is 20 seconds. And this is the time that the switch will wait to consider STP changed. And by default, the max age time is 10 times hello time. We have also the forward delay. Forward delay is 15 seconds, and this is the time between a change interface from blocking to forwarding. So if interface goes down in our topology, our switch will wait the 20 seconds. So during that time, if our switch didn't receive any hello message, it will wait until 10 messages not delivered to it. It will consider that there is a change on the topology. It will take 15 minutes also in order to move the plugged port to forwarding state. So when our switch starts to work, the spanning tree will start to do the election in order to choose the root bridge, the root ports, the designated ports, and the plugged ports. So the interfaces in spanning tree goes in specific states, and each state has its own features. So the states for the interface is blocking, listening, learning, forwarding, and disabled. In the blocking states, only the BBDU message will be sent, the root bridge will be chosen, and all the ports, the root ports, the designated ports will be in that state, and there is no forwarding for any frame. Any frame will be discarded. The blocking states take 20 seconds. After that, we have the listening state. In that state, the interfaces will keep exchanging BBDU message. The root port will move to that state. Also the designated port. There is no frame will be forwarded in that state. This state takes 15 seconds. After that, we have the learning state. In that state, the ports will exchange the BBDU message. Root port, designated port will move to that state. There is no frame will be forwarded. However, the interfaces on that state will start to learn about frame MAC addresses. This state takes 15 seconds. And after that, we have the forwarding state. Forwarding state will keep exchanging BBDU message. So the root port and the designated port will be in the forwarding state. This is a stable state. Our switch will start to forward the frame normally and will keep learning MAC addresses. So this is the last state. So we don't have any timer for that because the switch ports will stay on the forwarding state. Then we have the disabled port. The disabled port will block everything. The port will stay in the disabled state until something happens on the topology, and if anything happens, it will take the max age and forward delay in order to be in the forwarding state. This is the end for this video. Thank you for watching and see you in the next one.